Okay, we're back. Let's pick up with the other things you might see in a circuit diagram this year, other possible parts of a circuit. And it's these three in the middle that we haven't talked about yet. So far, we've got cells and batteries. They are power or voltage sources. We've got resistors, variable resistors, and lamps, energy consumers. We still haven't talked about switches, voltmeters, or ammeters. So let's draw the pictures for those, shall we? Let's focus here first of all. There we go. Okay. So we have switches. This is the symbol for a switch. Okay, right now it's in the off position. A switch that's in the on position, I usually just draw like a line like normal, but then just put like two little circles there to indicate that, hey, there's a little switch here. What a switch does, very obviously, it controls on and off to allow current to flow for either the whole circuit or part of the circuit. Okay? We don't deal with switches too much, but you should know that that's what they do. And they don't have to control the entire thing. They can control part of a circuit. We also have voltmeters. Symbolized by a circle with a V. And what this does, meter, it's not referring to a distance, it's referring to like a measure of something. What a voltmeter does is it measures potential difference between 2 points in a circuit. Remember, when we talk about electric potential, we're usually mostly concerned with the difference in potential from point A to point B. What is the difference or drop or gain in electric potential, which ultimately corresponds to how much energy has been lost or gained per amount of charge. Finally, the one other thing you might see is an ammeter, or you will see ammeters. You will definitely see voltmeters and ammeters. Switches you only see every once in a while. And remember what? It's got the same first two letters as amps. An ammeter measures the current in a circuit. Okay. So let's see all these things come together. So what I'm going to do is I'll show you exactly where I go to get this simulation. So I'm going to take the phone here. I'm going to go to the computer. Okay. Now, what we have here is if you Google PHET, you guys have used this simulation before, circuits. The first one that comes up is the Circuit Construction Kit DC. And you want to start it, and this will work on phones too, I did check this out. And you want to choose, you can see my reflection there, you want to choose the lab, okay? And what it does is it basically just gives you a sandbox. This is called a sandbox. Over here on the left are lots and lots of different things that you can put into circuits: wire, battery, light bulb, resistor. We're pretty much just going to stick with these four. You can zoom in and zoom out down here. On the right-hand side, it says show current, so we can actually pretend to see the current going around electrons or conventional current. I'll show you both of those. Labels for what all the things are, and also the values. I'll turn on values later on, but we don't really need them right now. There's also a voltmeter and an ammeter. And we can also change, and this isn't too important to you, wire resistivity and battery resistance. I'll show you both of those. Wire resistivity actually does matter to you now that I think about it. And then we can always go from real pictures down here to circuit diagram symbols. So, real quick, let's just make this very basic circuit. Let's make the simplest one we can, a power source connected by wires to an energy consumer. So our power source here is going to be the battery. I'm going to grab the battery, I'm going to drag it over. You can rotate the battery a little bit. Oh, I'm going to do conventional current for right now. Okay. And now I'm going to put a resistor over on the other side. Okay. Great. Nothing's happening. Well, obviously we don't have any wires. So I'm going to start connecting the wires, and you can connect the wires any way you want. I just kind of like to make this nice rectangular shape. I'm going to move everything up too, because I know what I'm doing here. Okay. Notice that when my circuit contains just wires and an energy consumer, I don't yet have a circuit. Okay, so just having these two didn't work out, and just having a energy consumer and wires didn't work out. I need all three in order to make the circuit run, and obviously, as you probably know, the circuit must be closed. Voila, look at that, there we go. Notice that I have some red arrows here, okay, and the red arrows represent conventional current. That's the assumption that positive charges are flowing. So that would mean this is the positive terminal of the battery, this is the negative terminal, and this part doesn't really happen here, but they're just oversimplifying, okay? This is a great simulation. It's not perfect, but it's absolutely fantastic for teaching the basics. So we have those red arrows that are moving, and if I click onto electrons, watch what happens. So this is what's actually, so this is conventional current. This is what we think of as happening because it's easier to think of positive charges flowing a certain way. If we instead think of electrons, look at that, the electrons are going the other way. This is actually what's happening. This is just what we assume is happening because we like dealing with positive charges more. I mean, be honest, would you rather deal with positive numbers or negative numbers? Positive, I thought so. So this is actually what's happening. This is what we assume is happening. Notice that I also have a voltmeter and an ammeter, so I can measure the voltage difference between 2 points in the current in the circuit. You can see that's a voltage difference of 9 volts. I connect the probes across like this. I can also measure the current by dragging this over. Okay, so now I can look at the current at any point in the circuit. There is another ammeter there, and I'll get into that in just a little bit. Okay. All right, so let's see. What do I want to do here? Because there's lots and lots of things I can show you with this, but I think right now we'll actually go back to the notes for just a minute. So I'm going to leave this. We're going to go back to the notes. And again, I mentioned this in the last video and you just saw it. Note that in real life, it is electrons that move from the negative to the positive terminal. However, when we discuss circuits, we pretend that the moving charges are actually positive and that they just flow the other way. And everything works out exactly the same. Okay, it's kind of like using a double negative in English. I can't, won't go. I cannot, will not go. Or no, that's a bad example. I don't not want to. I do not want to means essentially I want to. Okay? So positive to the negative terminal and positive charges are what we assume is happening. A couple other things to show you here. And we're going to start talking about resistance. It's a key topic for circuits. What happens if you only had wires connected to a voltage source, like a battery? Well, let's see what happens. Let's go back over here. Let's look at our circuit. Let's actually delete the circuit, so let's restart. And let's do a battery. And let's just connect the battery to itself with wires. See what happens. That seems bad. You have the charges moving super, super fast, and no matter what, whether it's conventional or electron current, and that battery kind of looks like it's on fire. So that doesn't seem good. So what this is called, if you know your electricity or familiar with this is called a short circuit. Okay? Essentially what you've done is you have created a current that is too big, okay? Remember, the different terminals of the battery, one's positive, one's negative, the electrons want to go, or the charges want to get from one terminal to the next. And if you don't put anything in their way to slow them down, they move way too fast. And you know what happens when things move really fast and they kind of rub up against each other, maybe against the sides of the wire? It creates friction and heat. So what you end up with is something that is you're generating too much heat, and therefore the battery, in this simulation, catches fire. So that's called a short circuit. You can't have just a battery and wires. You have to have something somewhere for the energy to go to get dissipated. Dissipated is a fancy word for given off. So this is a bad circuit. If you just have a battery connected to itself, There you go. With wires. Battery connected to itself. Energy is transferred too fast, and the circuit either explodes or catches on fire. Okay. So instead what we need here is we need a way for the energy to escape safely. Okay, we can't have the current flowing too much there. We need something in the circuit that will resist the current, something that will decrease the flow of electric charges, make it essentially harder for them to flow so that not as many are flowing at once. So, oh, sorry, I'm looking for something on here. There we go. I used to have a great video of a short circuit, and now I can't find it anymore. Oh, that's unfortunate. Oh well. Okay, you've seen what happens. Anyways, we need something in the circuit that will resist the current, something that will decrease the flow of electric charges to make the circuit safe and useful, because the circuit's not useful if the battery's blowing up. Every single thing you put in a circuit has this property of being able to resist the flow of electrons, and it's known as resistance. Okay, and the resistance of any part of a circuit is given by this equation. We're going to go back to the reference tables for a second. We're going to go to this equation right here. R equals V over I. R being the resistance, V being the potential difference, I being the current. So we're going to need to explain this a little bit. R equals V over I. V in this case is the potential difference before and after an object. Essentially, what it boils down to is how much energy this thing uses. Remember, V isn't the same thing as energy, but it's very closely related. It's essentially how much energy it uses per charge that flows through, and that's what we're doing right here. I is the current flow through the part of the circuit, through that object. Okay? An object that has some resistance, so objects with resistance use the energy that charges have or carry with them. So, how does a resistor use that energy that charges that pass through the resistor are carrying with it? It takes that energy and it dissipates it, gives it off as heat. A lamp gives it off as both heat and light energy. Okay? Another way of thinking about this is that charges must work or use energy to get through the object. So what this really means is you can imagine like putting a bottleneck on a road, okay? What the bottleneck is, it acts like a resistor. You're slowing the flow of cars that go through the road in order to make it safer for people to travel on the road. Imagine like a police stop or something like that. What a resistor does in an electric circuit is the same thing. It makes it harder for charges to get through. Charges must use some of their energy to get through the object. Okay? And what that does is it decreases the flow of electrons, the flow of charge through the object. Let's talk a little bit about the units for resistance. The units on top of voltage or potential difference are just volts. The units on the bottom for current are amps. So volts per amp, this is known as an ohm, O-H-M. He was a famous scientist. And the symbol is this weird looking horseshoe thing. That's a Greek letter omega. What this equation shows us, it shows us that each part of a circuit has a certain drop in potential difference inside that circuit. The resistance of an object is equal to the change in V, potential difference, how much the voltage drops, divided by how much current is flowing through that particular part of the circuit. So this equation shows us that each part of the circuit is associated with a drop in the potential difference or voltage in the circuit. A circuit component that has a resistance is associated with a loss of energy. So what I want you to think is when you hear the term voltage drop, what's really happening is that there is a loss of electric potential energy. Energy is being given off because charges have passed through this part of a circuit that has some resistance to it. The total voltage drop in a circuit is equal in magnitude to the voltage gain inside a battery. And this is an example of conservation of energy, and I will show you this in the next video.